So that's all the constructive interferences. Let's look at the destructive. Well, my first m is 0. I get 0 plus 1/2 times lambda, that's lambda over 2, right? That means d sine theta is equal to lambda over 2. That means the sine of theta is bigger than this theta, not 0. But it's also less than this theta, right? As theta gets bigger, the sine of theta gets bigger. They're directly proportional. So I've got some non-zero d sine theta, but I know that theta is going to be bigger than this, but also less than this. That means right in between there, I get a dark spot. Right? I can't draw a dark spot on the board, right? You see where I'm going with that. But right in here, there is a region of, let's do this, complete destructive interference, which means I get a dark spot there. So bright spot, dark spot. Bright spot, you guessed it, it's dark spot. This dark spot corresponds to m is equal to 0. Just like this bright spot corresponds to m is equal to 0. So both of these actually correspond to m is equal to 0. This corresponds to m is equal to 1. So does this one. That's what happens when I put in m is equal to 1. I get d sine theta is equal to 1 plus 1/2. 3/2 lambda. That's my next half integer multiple. So this is m is equal to 1. And there's more, right? There's a dark spot right here corresponding to m is equal to 2, and so on and so forth. Does that make some sense? Now what about the negatives? Well, turns out there's a sequence on the bottom. Right? There's a bright spot here, there's a bright spot here, bright spot here, right? If this is my reference angle for theta is equal to 0, coming down here gives me negative angles. Where's where those negative numbers come from? We don't usually worry about these. They're there. I'm not going to ask you to calculate anything with them, so you can kind of forget that the negative signs exist. But you should not forget that there's another sequence of bright and dark spots down below the horizontal. Those are where the negative signs come in, right? So this is m equal to -1, -2, yada, yada, yada. Okay? M is called the order. This is where things can get a little confusing depending on what text you're using. Different texts follow different conventions. Here's how I'm going to do it. I'm always going to match up the order with the m number, right? That's kind of a problem. I mean, not kind of a problem, but people do it another way. I'll tell you how other people do it, so don't write this down. This is not what we're going to do. They might say that this is the first order bright spot, right? So first order corresponds to m equal to 0. They might say that this is the second order bright spot, which corresponds to m is equal to 1, third order. I find that very confusing. Right? So I use the term 0th order, not just me. I didn't make this up. Some textbooks do this, some textbooks don't. So I'm going to call this the 0th order. Right? Strange word, 0th. But it's okay. There's a 0th law of thermodynamics you'll study when you get to thermo. 0th is okay. So 0th, first, second. So this is the 0th order. This is the first order. This is the second order. So when I say second order, you immediately know m is equal to 2. You don't have to worry about any of the subtracting. Okay? Now be careful. This is the 0th order bright spot. This is the 0th order dark spot. Right? So 0th order dark spot is m is equal to 0. The problem is a lot of people ask that question differently. Where is the first dark spot? Right? They didn't say first order, they said first. That's confusing and annoying. I won't do that to you, but you will see it in other places. Right? First dark spot, I would say, would be this one. Right? But that's the 0th order. So you can't really escape all of the confusion no matter what we do with it, but that's okay. If you need clarification, you can ask. But I won't use those words, but some people do. Does that make some sense? All right, let's do an example. Or a slip of distance d is equal to 800 nanometers. What does nano mean? 10 to the negative 9. Yes. Slit of distance. No, I don't want to do that. Let's go. Yeah, do it. 800 nanometers. What angle produces the first order bright spot? Okay. So here's what we have. First of all, let's ask ourselves this question. Do I need the constructive equation or the destructive equation? Constructive. What led you to that conclusion? Bright spot, right? Sometimes they'll say maximum, bright spot, bright fringe. All of those words are used to mean the same thing. That's the maximum. That's where the constructive interference occurs. So, picking out this one. All right, let's write that down. D sine of theta is equal to m lambda. Now, what value do I put in for m? I know lambda, m is given to me, d is given to me. No, lambda is not given to me. .632 nanometer light, I'm sorry. You gotta know what color light we're dealing with, right? Okay. 632 nanometers is a red laser, basically, in case you keep track. That's the usual wavelength of red lasers in this country. Okay, so d sine theta. So I know lambda, I know d. What is m? 1. What led you to that conclusion? First order. I'm going to match that. So I know everything except for theta. Let me just go ahead and solve. Sine of theta is equal to m lambda over d. Yep. And that means theta is equal to the inverse sine of m lambda over d, which is equal to the inverse sine of 1 times 632 Yeah, 632 nanometers divided by 800 nanometers. Do I need to convert nanometers to meters to do this? No. Why? Yeah, arguments of trigonometric functions have to be dimensionless, right? So as long as all of your units are the same, they're going to cancel. Now what you can't do is put in nanometers and femtometers, right? You got to have to convert something. As long as your units are the same, they're going to cancel, which they have to for arguments of trigonometric functions. All right. I didn't pull this up. (632) divided by 800. I get 52.19 degrees. Just that simple. It's pretty straightforward. Any questions about what we just did? Okay, so let me ask you this, if that's okay. At what angle is the second order bright spot? How would I do that? Replace the one with the 2. You might see a problem there.
Are you talking about like upwards or downwards?
Well, Sylvia's question was upwards or downwards, either or. If you can do the upwards, the downwards is literally the same thing, so I'm not even going to worry about the downwards. So I'm not worried about the negatives at all. So we'll just assume everything's positive. What's the problem you see if I put 2 in there? That's out of bounds of the sine function, right? You're going to get the 1264 over 800. That's bigger than 1. Sine of theta can't be bigger than 1, right? So is there a second order bright spot? No. That's important because the series, all of these series truncate at some point, right? All of them truncate at some point. And that's another really common question. So we're going to investigate how to do that, but first, any questions about how you proceed here? This is pretty straightforward. I should say, this works also with multiple slits. If you have what's called a diffraction grating, it's basically a piece of plastic with a bunch of lines scratched on it to act like a prism. The same formula works. Just usually there's some work on the front end to figure out the distance between the lines. In that case, they're not slits, they're lines. Because you're normally given diffraction gratings with like an 8,000 lines per centimeter. You got to flip that around to figure out the distance between the lines. But that's simple algebra. Once you get that, it's exactly the same. There is also single slit diffraction, which we are not covering. It's in your book if you want to look into it. It's similar, except the functions are switched. What was constructed is destructed for that, and vice versa. It's not that important. I'm not going to get into it. But you will see perhaps some problems with multi-slit diffraction. Works the exact same way. Same formulas and everything. D is just the distance between the slits. Okay. All right. So how to find max order. Let me do this. Let me change this to 3,000. That should be decent enough. 3,000 nanometers now between my slits. So my question now is, what is the maximum order for this system? In other words, where does the series truncate? What angle is the last bright spot I see? Okay, so I'm still looking for a bright spot here. I said maximum order, that means the highest M value. But to find that, we're going to assume constructive interference. Which means I still have this expression. D sine theta is equal to M lambda. And what I'm looking for is the highest value of N. Right? Anybody see a way we might proceed from that? If I need to maximize something, what's the easiest thing in here to maximize? Sine theta, right? I can't maximize D, that literally goes on forever. M is an infinite series. Lambda can be as big as I want to. The only thing you can maximize in here is sine theta. What's its maximum? Let's try that. Let's solve this for sine of theta is equal to M lambda over D. And then if I'm looking to maximize things, right, D and lambda are set. Nothing will change there. But what I'm looking for is the value of M that gets me a maximum value on the left-hand side. But you've already told me the maximum value on the left-hand side is 1. So that's really simple. Just set it equal to 1. Right? Now, solve for M. D over lambda. D is 3,000 nanometers. Lambda, 632 nanometers. If I plug this into my calculator, I get 4.75. What's my answer? What's my answer? What's your instinct when you see 4.75? 4. Yeah, 4. Right? Can only be 4. M can't be point anything, right? M is an element of a set of integers. So when you find this, you just get rid of the decimals. Do you round up? No, because M is equal to 5 gives you nonsense in this equation. So you round out. It's very similar to what you probably did in 1600 when you're doing Archimedes' principle and you said 17, or a certain amount of students board a raft. How many can you put on till it sinks? And you found that 16.3 you're like, well, who are you going to cut in half, right? So always round down. We're looking for integer values here. We don't round up because if we're already maximizing, we can't go any higher. Even if it's 4.9999999, the maximum value that n can be is 4. All right, does that make some sense? Okay. That's pretty straightforward. Any questions about any of that before we do another kind of interference? So 2 of the questions on your homework involve this stuff. I believe one of them asks you to find a bright spot. Other one has to do with the dark spots. So just keep the orders in mind and ask questions if you got it, okay? Any other questions about this? All right. Last real topic of the semester, I suppose. Thin film interference. This is slightly more complicated than what we just did. But the principles are the same. The principle being path length difference determines interference. Because that's what's putting the waves out of phase. Alright, so a thin film is just that. It's a film of something that we can consider to be quite thin. Okay? So, let me give you something that doesn't look thin. So what I'm doing is I'm blowing up something like a soap bubble. A soap bubble is a thin film. Oil floating on water was usually probably considered a thin film. Alright, so this doesn't have to be a soap bubble, but let's assume that it is, right? So that means up here is air. A soap bubble, for our purposes, is basically water. It's what it is, right? The reason it forms a bubble is because soap, the presence of soap lowers the surface tension of water so that it doesn't collapse into a little droplet. It's able to spread out. That's what surface tension. Water is very attracted to itself. It's called surface tension. If you can break up the surface tension, you can allow it to form larger structures like bubbles instead of collapsing into small droplets. Right? So it's basically water. A soap bubble is basically water. So I have air up here, water here, and inside the soap bubble I have air here, right? So this is a thin film, much thinner than I've drawn it. It has a thickness of T. I really don't like using T. T in my mind is reserved for time. But that's okay, we'll use it. T for thickness in this case. Right? It has a thickness of some T. Alright, let's put some light on this and see what happens. So I should point out, I'm going to draw this light coming in at an angle. The effect we're talking about is most observed when light comes in straight down. But then if I do that, you can't see what's happening. So I'm making the approximation that we're coming in at an angle. But generally, if I were to draw it correctly, it would be coming straight down. Okay. Alright. Light comes in. Hits a boundary between media. What happens? Refraction. Yeah, close. It's okay. Well, part of it is transmitted, part of it is reflected. Right? And we've studied that already. So the reflected light will look like this. The transmitted light will go something like this. Right? Uh-oh, there's another boundary. What happens? Same thing. I'm not going to worry about the part that's transmitted. It happens, but I'm not going to worry about it. I'm going to worry about the part that's reflected. Back up. Another boundary. What happens? Well, the same thing. This time I'm not going to worry about the part that's transmitted. I'm going to that's reflected. I'm going to worry about the part that's transmitted. So this is put out like that. Right? So I'm definitely leaving off what's transmitted here and what's reflected here. It just doesn't matter to me. Because now look what's happened. I've got 2 rays of light that are going to propagate that way and hit my eyeball. These rays of light have now taken 2 different paths, which means there is a propensity or a potential for interference. All right? What's the path length difference between these 2? Well, if I remember that I'm really talking about systems which come in straight down and leave going straight up. Right? That is a path length here of 1t, 2t. Right? My path length difference between these 2 rays, I'm going to approximate as 2t. That enables me to say immediately, all right, well, how does that match up with my previous stuff? Path length difference. which used to be d sine theta, but now it's 2t. I have two possible ways this can work out. M lambda, m plus 1/2 lambda, right? One of those is going to give me constructive, one of those is going to give me destructive. I haven't written down which one on purpose, so you shouldn't either. But do you see what's going on here? That path length difference is going to put me in one of these two camps, or at least it can put me in one of these two camps. It could be an integer multiple of the wavelength, it could be a half integer multiple of the wavelength. Okay? Alright. Now, there's some complications that come in. First thing, these actually have different wavelengths out here and in here. To see why that's the case, let me ask you this. Earlier in the semester, I had some lasers and I was shining them into lucite and glass, and I don't think I showed them into water, but you can. Did the color of the light change inside the lucite? If it was a green laser on the outside, when it got into the plexiglass, did it change color? No. Still green. Did not change color. Okay. What does that mean? Well, in light, frequency is associated with the color. Right? Frequency is also associated with the energy. That's why the color doesn't change. It's an expression of the conservation of energy. We don't expect the energy content of the light to change as it moves from one medium to the other. Right? Where would it go? Where would it pick up some? Right? We don't expect the energy content to change. But what the color then shows us is that the frequency actually doesn't change. Okay? So the frequency is constant. But here's the other thing. What about the speed?